In the previous lesson, we talked about sliding contact bearings. Sliding contact bearings. And you notice that there we had issues with friction, also dealing with journal bearings, because when we talk sliding contact, what comes in mind is it's the journals. So that's why we picked the principles under journal bearings. Now, here we are going to talk about rolling contact. And the difference is very clear because when you talk about rolling, you're talking about a member that is moving. And even the area of contact in this case is different from a sliding contact. But let's see some principles attached here before we get to work. So here is where we're saying that these bearings, unlike the other type, the rolling contact bearing are designed to handle a different kind of loading compared to the other one. For sliding contact, that is where you see a lot of sliding coming in. But with this one, you'll see that even the loads, dynamic loads that are involved can even be at very high speeds because of their rolling action. And with sliding, what you might have already seen is that the surface area that is involved is large. But for rolling, it will be quite small because the contact is much smaller, which also gives some other disadvantage, but as well as providing advantage because this is the bearings normally handle dynamic loads. So we need that to be really put under a lot of control. Now, what advantages do you see? One of them is that the friction is reduced compared to the sliding one. And they are also able to withstand those shock loads. The low maintenance costs, we talk about relatively small in size, easy to install and uninstall. They are also clean and reliable. Then what is the bad side? What are some bad sides to this? At very high speeds, they can be noisy. And with prolonged shock loads, the resistance also goes down. Now, here is where I wanted it to. When you talk about these rolling contact bearings, they have some precision drama. So you find that the housing design, the tolerances involved can be quite something. So this comes in with that's why here it says that they are complicated bearing housing design because of those parameters. A rolling contact bearing can be expensive. Unlike a sliding bearing, which is similar to a bushing, this one you need to spend a bit of some money because you have some inner race, outer race, the cartilage there, and also the rolling members in between. There could be rollers or maybe some balls or something. Then you see them working. So types of rolling contact bearings. So with rolling contact bearings, we have ball bearings as well as roller bearings. That's just the main part. Now, rolling contact bearings use rollers. Ball bearings use those balls in there which are able to rotate and they're able to, they are accommodated between the inner and outer race and supported by the cartilage so that they don't hammer into each other. So we have what is known as basic static load rating or rolling contact bearings. So this one is normally the static radial load or axial, which corresponds to the total permanent formation of the ball or roller and race. That is at the most heavily stressed contact equal to 0.0001 times the ball or roller diameter. So meaning that the static radial load rating, CO, if you look at the formula, it is CO is equal to F IZD squared, where CO, of course, we already said that the static load rating. I is the number of rows in the ball or bearing. Z, number of balls per row. Then D, diameter of the balls in millimeters. Alpha, nominal angle of contact. FO, this is another constant, which normally depends on the type of bearing you're dealing with. So for hardened steel ball, that constant FO is 3.33 and 12.34 radial for angular groove bearings. Then for radial roller bearings, the static load rating is F4 IZ, then LED, then we have cos alpha. So here we include the cos alpha at the far end. Of course, in this case, like we had said earlier, I, number of rows of ball in a bearing, Z, number of balls per row, LE, that's the effective length of contact between the roller and the ring. Then D, diameter of the roller in millimeters, alpha, nominal angle of contact, and FO is just a constant, meaning that if you are dealing with hardened steel balls, this will be 21.6. Thrusts, bearings, load rating for them, it's the only difference we can see is here we have F, then the Z, D squared sine alpha. Like we've shortened some things there. Why? This is the thrust bearing, a different type. So FO can be 49, and of course Z is just number of balls carrying the thrust in one direction. D, of course, is supposed to be the diameter that we are referring to. Then what about roller bearings? Thrust roller. The other one was for ball bearings, thrust ball bearings, but this is for thrust roller bearings. This one, unlike the radial roller, here we use sine alpha. The rest on the other end are almost the same, except there's no I. So FOZLE sine alpha. Z, number of balls carrying the thrust in one direction. FO 98.1 if it's hardened steel. Static equivalent load rating. So this one, we're talking about the load or actual load or static load, which would cause the same total permanent deformation at the most heavily stressed ball or roller. It's like talking about the weakest point in your bearing. Now, away from that, let's talk about the life of a bearing. The life of a bearing, this one, it can be either in revolutions, how many revolutions a bearing can go through, or how many hours it can go through before it fails, or before fatigue kicks in. That is the life of a bearing. That is the life of a bearing. Then we continue, we're talking about you baby, my light here in the cool. Akata kari ganga na, okatila wonke ya salama. Então, kama sote. Chipozinga twautukati. Okay, let's continue. So here we're talking the life of a bearing. In the life of a bearing, we have one thing that we refer to. We look at the factors involved. We say it can either be how many hours is this bearing going to last before it can give in, or how many revolutions is it going to turn through before it can kick in, it can give up, fatigue can overcome it. So then we go back to dynamic load rating. Dynamic load rating. So this is the projected or approximate rating or service life of a ball bearing, ball or roller bearing. We'll see the difference in the constants involved. So how do we do it? We determine it using this expression here. L is C over W, then power K times 10 power 6. Then C, if you're now trying to find C, you can make it the subject of the formula. And what you have now is Z, W in the brackets L over 10 power 6, then power 1 over K. You don't need to worry about all this. We're just building up basic dynamic load rating. Then we also have W equivalent dynamic load rating. Then we have K. So K, this is where you now see the demarcation between ball bearings and roller bearings. For ball bearings, the value for K is 3. For roller bearings, the value for K is 10 over 3. Of course, we know 10 over 3 is 3.3333. So that's like what makes them stand out between the two of them in terms of this constant K. So what is the relationship between the life of a bearing in revolutions and the life of a bearing in hours? It's that formula there. L is 60N LH. So in case you're trying to convert either way or backwards, you can always refer to that expression. Now, sorry, this moved a bit fast. So if a bearing is operated at a constant load W1, meaning it's just running at one load, then your L1 is C over W 1 or K, then multiplied by that constant there. Then if you now bring the fraction between the life of a bearing, because the life of a bearing is given by L, then N for N evolutions. Here you can say N1 over L becoming N1 W over C, then power K. Then everything divided by 10 power 6. Meaning that if I do the same, if I go to load number 2, which is for N2 revolutions, I'll just change where I have 1, 1, I put 2, 2. So I have N2 over L2 being equal to that N2, then W over C power K, then 1 over 10 power 6. We can go on. We can also have about 3, 4, like that. Now, what are you seeing in this sequence? These are fractions. So if I now just take the right-hand side, I can see that if I decide to add this to that, the next one, I can have N1 over L1 plus N2 over L2 plus N3 over, I can continue like that, N4 over L4. Whatever I'll get, the total I should have is 1, because the fraction 1, meaning in percentages, it's like I'm now going to 100%. Then Additionally, if I decide to add what is on the right-hand side, I will add this where I have the 10 power 6. So I'll start with the N1 here, N1, CW1 over C, 1 over 10 power 6, which is this one. Then I bring this one also, N2, W2 over C, then 1 over 10 power 6, plus N3, W over C power K, then 1 over 10 power 6, plus I was going to have N4, it's N4, like this, N4, then in the brackets, I just change where there is a W, where there is 3, I'll put 4. Then C is okay, over C. Then in the brackets, everything, raised to power K. Then I have 1 over 10 power 6. Then I have 1 over 10. 10 raised to power 6. So this is my 10. And it's being raised to power 6. I can go on. I can also say plus. Where I have 4, 4, I put 5, 5. The rest remain the same, just like that. So with all this, I can already see that if I decide to simplify so that I get rid of the denominators, let me take you back to what the denominators are saying. What are the denominators? The denominators you can see here, there is this 10 power 6. At the same time, you can also see C, 10 power 6 and C. So 10 power 6 and C, if I multiply through by those, I'll just remain with N1 W1 K plus N2 W2 power K plus N3 W3 power K, just like that, N4 W4 power K, and it continues. Everything being equal to 10 power 6, then the CK, because here the denominator is basically having almost the same thing. The C, the constant C and 10 power 6, those, they are not changing. That's why we may decide to do this. Then on the other end, you have that. Because we said all this on the other end is supposed to be equal to 1. So no, now this time around, the 1 is out. This is what we have. So then, suppose we have the equivalent load rating W acting for n evolutions. We say N is C over W power K by 10 power 6. That's what we already picked, meaning if I open these brackets, it's C raised to power K and W raised to power K because this power belongs to both of them. And then there's 10 power 6. So that is why I have NWK. Here it's like we're trying to explain where this came from. Then 10 power 6, then there's a K. This becomes like our equation number 2. Equation number 1 was that. So this, with this in mind, we proceed. So we're saying that the total value for n should be when we add all those n's, n1, n2, n3, n4, n5, up to whatever number we have. So since we already know that on the right-hand side, the total should be 1. So we can equate those two equations that this, what we have here, should be equal to what we have simplified right here. Because this is equal to that. This is equal to NW power K. So having done that, we can make W now the subject of the formula from there, which gives us now W is N1 W1 power K, N2 W2 power K, just like that, over N. Meaning that we're going to have one load. Then these will be the various loads at various percentages or speeds or, yeah, so we'll be able to combine them. That, for example, this machine was running at 20% of the time. At what speed was it running? Maybe it was running at 500 RPM, carrying a load of so much. So we'll take into consideration all of that. Then K is a constant, which you already know. So when we substitute the final expression, the value of N, remembering well that we said N is supposed to be equal to all this. So we just bring this and plant it there. Then gives our value for W that we are looking for. So there, W is in case you decide to use L, where there's N, just put L and the rest continues like that. Reliability of a bearing. So this one talks about the ratio of the number of bearings which successfully complete L million revolutions to the total number of bearings under test. So that's basically a ratio. And this therefore starts like this. You have, first of all, log E, 1 over R, R referring to the reliability, then L over A on the right-hand side. A and B are constants. L is the life. So then this can also be expressed in this format where we're saying L over A is equal to log E, 1 over R, then raised to power 1 over B. So A, the value can be 6.84, B can be 1.17. Then if, for example, we have L90, we're talking about the life of a bearing with 90% reliability. So that's like reliability 90 is life at 90%. So R we put 90, for L, the same thing. So what do? We have L90 over A being equal to what we had earlier. Now comes the equation we're looking for. So we can have L over L90. L being the one we're looking for, it could be the one we want to subject. Then L is equal to log E, 1 over R. Then over log E, 1 over the R90 that has been specified. Then everything raised to power 1 over B. All right, enough of the analysis. Let's get to application. We've moved around a lot of those formulas, but we can't just end there. Let's now try to go to the application. So here we have a shaft rotating at a constant speed subjected to a variable load. Now look at the way the loads are. So the bearing is supporting the load. The bearings supporting the load are subjected to a stationary equivalent load of 5 kilonewtons. Just a minute. At 10%. Okay, here. Let me just try to move this a bit. Is it going to? Aha, okay. Yes, it can move. 10% of the time and 6 kilonewtons for 10% of the time. And we've also been given 2 kilonewtons for 40% of the time and no load for the remaining cycle. No load for the remaining cycle. If the total life expected for the bearing is 30 by 10 or 6 revolutions at 95% reliability, determine the dynamic load rating of the bearing. So we need to find out the dynamic load rating for this bearing. So what are we going to do? First things first, I want us to look at the percentages. There is 10% of the time at 5 kilonewtons. So 10, then 20% of the time at 6 kilonewtons. If you add 10 and 20, you get 30%. Then 2 kilonewtons at 40%. So what I have now is 10 plus 20 is 30. Then 30 plus 40 is 70. If I remove 70 from 100, it means I'm remaining with 30%, which tells me that at 30% of this time, at 30%, at the remaining 30%, this bearing was running rather at zero load, at no load. So it was actually operating at 0 kilonewtons. 0 kilonewtons. Can you imagine? At 30% of the time, we're running at 0 kilonewtons. That's how this has worked out. So with that in mind, let's just try to look at how this information is flowing. Data provided. First, load number 1, which is W1, 5 kilonewtons. Then N1 is 10% of the total. So I'm going to call it as 0.1 N. Remember, N is the total and N is supposed to add up to 1. So 0.1 N, 0.1 of that total time. Where do I get the 0.1? It's 10%. It's actually 10 divided by 100. Then I have that. W2 is 6 kilonewtons. I'm leaving them in kilonewtons, so no problems, because even the answer I'm going to find should also be in kilonewtons. 6 kilonewtons. For N2, I have 20% of the time. So 20 divided by 100 gives me 0.2 N. N2 is 0.2 N. And W3 is 2 kilonewtons. How much time? It's actually 40%. So 40 divided by 100. 40 divided by 100, which is 0.4 N. So if you want here, you don't need to write 0.4. For those of you enjoying mathematics, you can write it in full, 40 over 100. Then you put the N there. It's the same thing. The interpretation will still be the same. Let me proceed. The fourth load was actually W4. We were told it's at no load. Most of you have those interesting answers, questions that you like asking. Suppose there was a number here, it didn't say no load. What were we going to do with this value we've put here? Here they have said no load, meaning that there is a number. The number is 0. So if there was a different number provided there, that's what we were going to write there. It's as simple as that. No need to stress. So if this is number 4, number 4 is the one I was analyzing here. It's for the remaining time. The remaining percentage, because all this took up 70%, all this took up 0.7. Meaning I remained with 30%, which is like 30 over 100, giving me 0.3. So hence I have 0.3 N. So that's my N4. Then B, this is the constant, standard constant 1.17. Then we have life of the bearing at 90%, 95% reliability. So that's the one we're calling L95. It's 30 by 10 power 6 revolutions. So now let's find the life of the bearing at 90, as per standard, at 90% reliability. Because this is the one which is the one we usually pick when we're trying to determine. So L90, like you saw in the formulas, L90 is one of those. So where we had L, we'll put L95, then the L90 will be put into question. Okay, here's our working. So first things first, L90 over L95. The formula was L log E, then 1 over R95. So here, in the formula, we just had 1 over R, meaning we can put the number in question. Then below here, we had 1 over R90, which is a standard because it has to be there. Then this one will feed into what has been provided. So 1 over R95, then raised to power 1 over B. So what do I do then? Log E 1 over R95, it's actually 0.95, it's 95%. 90%, it's C 0.9. So I have 1 over 90. Then B we said is 1.17. So I have 1 over 1.17. Then what do I have? I have L95 over L90 being equal to 0.54. L95 over L90 being equal to 0.54. Now, if you look at our question, we already had this. The life of this bearing at 95% reliability is 30 million revolutions. Yes, bearings can go this much. They can be in millions like that. In fact, we count them in millions because they are rotating all the time. So 30 million revolutions, that's what you have as the life. Now at 95%, so we want the L90. So you can just go there and substitute. In place of L95, you put 30 million. Then you put back the L90. On the other end, I still have 0.54. Then making L90 the subject of the formula, basically it's like I end up dividing this into there. So what I have is 505.56 revolutions. That is the life expectancy, the life of this bearing at 90% reliability. You can see that it has even gone up. 95% or smaller. 100%, it will even go lower. So anyway, this is how the numbers are. So I have the L90 because from that expression, I have gotten it. Then from there, let me go to the load rating. The dynamic load rating, we say W is N1 W1 per K, N2 W2 per K, N3 W3 per K, plus N4 W4 per K, plus N. We continue like that. Then below there, we divide by N, which is when you break it down, it's N1 plus N2 plus N3 plus N4 plus N5 plus. You continue like that. So in this case, there are 4. So meaning here, you should also include N4. Or we were given 4 loads, including the 4th one, which was at 0. Even in this, we include another one there for the 4th. So in my substitution, N1 is 0.1 N. The load was 5 kilonewtons. So 5 raised to power 3. The K for 3, the K was given as 3, looking at the nature of the bearing. Then plus N2 was 0.2 N, multiplied by the load at that point. The load at this one, at this one was 6. The power is still the same. Then the third one was N3 was 0.4 N, because it was at 40% of the time. Times, it was actually 2 kilonewtons as the load, so 2 raised to power 3. Then the remaining time was actually 30%, which is 0.3 N, multiplied by, we thought this was at no load, so it was 0 raised to power 3. And this is why I was saying that if you want, you can, equations will not always be the same. There could be a different number there. Whatever number is there is what you use here. What about this? Now we can add the n's. 0.1 n plus 0.2 n plus 0.4 n plus 0.3 n. Now, I don't even know why we're struggling here. I mean, why we're even wasting our time here, because 0.1 plus 0.2 is 0.3. 0.3 plus 0.4 give us 0.7. 0.7, when you add 0.3, you get a 1. So whatever is happening below here is 1, and there's n. Then when you add everything, all those products on top, you get 58.1 n. So the n will cancel because all of them are having n. You can even decide to, first of all, factorize it and remove it from there. Then you just have the numbers. So what I have now is 58.9 raised to power 1 over 3, giving me a dynamic load rating of 3.89 kilonewtons. Now with this, the dynamic load rating I have is here, where I have C is equal to W L90 over 10 power 6 raised to power 1 over K. You can see that we calculated W there. We also calculated for L90. So what do we do next? We substitute. My C is equal to 3.89. I mean, W is 3.89. L90 is 55, 555.56. Then I have 10 power 6. Everything raised to power 1 over 3. So from there, I have my dynamic load rating as 3.816. Now remember, all these numbers you are seeing here are in kilonewtons. And this is where I said, even our final answer will still end up being in kilonewtons. Even this one, therefore, was in kilonewtons. So we substituted a number here which was in kilonewtons. So therefore, our answer there is also in kilonewtons. There you are. You can also attempt that exercise and see how this works out. Then feel free to bring out issues as they come. Thank you very much. We meet in the next lesson, and feel free to bring up where you feel there's need for clarity. Post a comment or reach out to my inbox.